Assalamualaikum, Encik Kiwirizam bin Muhammad Khair. My name is Adli Osman bin Adnan and my metric number is 01 DKM19F1134. Introduction for intercooling gas turbine cycle. Number 1. Multi-stage compression with intercooling improves the efficiency of a compression process. A Brayton cycle with intercooling use 2 or more compression stage with 1 or more intercoolers as shown below. The power requirement for compression is reduced but QH also increase.
My name is Vikram Kumar. My metric number is 01 DKM19F1130. Working principles of intercooling gas turbine cycle. Net work output from gas turbine cycle can also be increased by reducing negative work, as an example compressor work. Multi-stacking of compression process with intercooling in between is one of the approaches for reducing compression work. It is based on the fact that for fixed compression ratio is higher is the inlet temperature higher shall be compression work requirement and vice versa. Schematic for intercooled gas turbine cycle is given in figure. Thermodynamic process involved in multi-stage intercooled compression are shown in figure. First stage compression occurs in low pressure compressor LPC and compressed air leaving LPC at 2 instant to intercooler where temperature of compressed air is lowered down to state 3 at constant pressure. In case of perfect intercooling, the temperature after intercooling is brought down to ambient temperature. As an example, temperature at 3 and 1 are same. Intercooler is a kind of heat exchanger where heat is picked up for high temperature compressed air. The amount of compression work saved due to intercooling is obvious from PV diagram and shown by area 2342 area. 2342 gives the amount of work saved due to intercooling between compression. Some large compressors have several stages of compression with intercooling between stages. Using of multi-stage compression with intercooling in a gas turbine power plant increases the net work produced because of reduction in compressor work. Intercooled compression results in reduced temperature at the end of final compression. TS diagram for gas turbine cycle with intercooling shows that in the absence of intercooling within same pressure limits, the state at the end of compression would be too wide. With perfect intercooling, this state is at 4. As an example, T2 is greater than T4. The reduced temperature at compressor exits leads to additional heat requirement in combustion chamber. As an example, more amount of fuel is to be burned for attaining certain inlet temperature as compared to simple cycle without intercooling. Thus, intercooled cycle thermal efficiency may not increase with intercooling because of simultaneous increase in heat addition requirement. The lower temperature at compressor exit extends the potential for regeneration, so when intercooling is used in conjunction with regeneration, an appreciable increase in thermal efficiency can result. Network output in gas turbine cycle with intercooling.
Assalamualaikum, my name is Alif Farhan bin Humain and my matrix number is 01 DKM 19F1133. So this is diagram of figure. Intercooling gas turbine cycle.
Okay, my name is Muhammad Iqbal Irfan bin Masdari. My matrix number 01 DKM19F1131. Okay, for summary of intercooling gas turbine cycle, the addition of intercooler in gas turbine cycle reduce the compression work, and this is achieved by dividing the compression processes into 2 or more stages, and the exit air or gas from each stage is cooled by the intercooler heat exchanger to the minimum cycle temperature.
Okay, my name is Muhammad Imran bin Saimi. My metric card number is 01 DKM F1132. Okay, for the next title is conclusion. Okay, overall intercooling gas turbine cycles possess inherent advantage of simplicity and flexibility of design and installation. Next, the intercooling gas turbine power plant has evaluated using thermodynamic principle and the technical data of the plant.
Introduction for reheat gas turbine cycle. A reheater is a heat exchanger that increases the power output without increasing the maximum operating temperature, but it does not increase the efficiency of the cycle.
Working principle of reheat gas turbine cycle. C is represent compressor, CC is represent combustion chamber, G is represent generator, F is represent fuel, HPT is represent high pressure turbine, LPT is represent low pressure turbine, RCC is represent reheat combustion chamber. Reheat gas turbine cycle arrangement is shown in figure. In order to maximize the work available for the simple gas turbine cycle, one of the options is to increase enthalpy of fluid entering gas turbine and extend its expansion as to the lowest possible enthalpy value. This can also be said in terms of pressure and temperature values. As an example, inject fluid at high pressure and temperature into gas turbine and expand up to lowest possible pressure value. Upper limit at inlet to turbine is limited by metallurgical limits, while lower pressure is limited to near atmospheric pressure in case of open cycle. For further increasing in network output, the positive work may be increased by using multi-stage expansion with reheating in between. In multi-stage expansion is divided into parts, and after part expansion work, fluid may be reheated for getting larger positive work in left out expansion. For reheating, another combustion chamber may be used. Here in the arrangement shown, ambient air enters compressor and compressed air at high pressure leaves at 2. Compressed air is injected into combustion chamber for increasing its temperature up to desired turbine inlet temperature at state 3. High pressure and high temperature fluid enter high pressure turbine HPT for first phase of expansion, and expanded gases leaving at 4 are sent to reheat combustion chamber reheater for being further heated. Thus, reheating is a kind of energizing the fluid, assuming perfect reheating, in which temperature after reheat is same as temperature attained in first combustion chamber. The fluid leaves at state 5 and enters low pressure turbine LPT for remaining expansion up to desired pressure value. Generally, temperature after reheating at state 5 is less than temperature at state 3. In the absence of reheating, the expansion process within similar pressure limits goes up to state 4. Thus, reheating offers an obvious advantage of work output increase. Hence, constant pressure lines TS diagram diverge slightly with increasing entropy. The total work of the two-stage turbine is greater than that of single expansion from state 3 to state 4. Here it may be noted that the heat addition also increases because of additional heat supplied for reheating. Therefore, despite the increase in network due to reheating, the cycle thermal efficiency would not necessarily increase. Let us now carry out a standard cycle analysis.
This is the diagram figure of reheat gas turbine cycle.
For summary of reheat gas turbine cycle, the reheat cycle increases the turbine work and consequently the network of the cycle. This is accomplished not by changing the compressor work or the turbine inlet temperature, but instead by dividing the turbine expansion into 2 or more parts with constant pressure heating before its expansion.
Okay, for the next conclusion is, from what we can conclude is the reheat is much more suited to combine cycles. The reheat gas turbine cycles is implemented, which can have a large effect on the engine output.
Introduction for regeneration gas turbine cycle. A Brayton cycle with regeneration uses a heat exchanger called a regenerator to preheat the air-fuel mixture before it is fed to the combustion chamber using the turbine influence as the heat source. A regenerator reduces QC and QH for the cycle by the same amount. This has no effect on the power produced.
This is the working principle for the regeneration gas turbine cycle. In the earlier discussion, it is seen that for the maximization of specific work output, the gas turbine exhaust temperature should be equal to compressor exhaust temperature. The turbine exhaust temperature is normally much above the ambient temperature, thus there exists potential for tapping heat energy getting lost to surroundings with exhaust gases. Here it is devised to use this potential by means of a heat exchanger called regenerator, which shall preheat the air-relieving compressor before entering the combustion chamber, thereby reducing the amount of fuel to be burned inside combustion chamber as a combustor. Regenerative air standard gas turbine cycles shown here in figure A has a regenerative counterflow heat exchanger through which the hot turbine exhaust gas and comparatively cooler air coming from compressor flow in opposite direction. Under ideal conditions, no frictional pressure drop occurs in idle fluid stream while turbine's exhaust gas gets cooled from 4 to 4, while compressed air is heated from 2 to 2. Assuming regenerator effectiveness is 100%, the temperature rises from 2 and drop from D4 to 4 is shown on TS diagram. This is the diagram of regenerative effectiveness, and where H refers to specific enthalpy values. Thus, thermodynamically, the amount of heat now added shall be Q8, region M H3 minus H2. Whereas without regenerator, the heat added Q8 the same as M H3 minus H2. Here it is obvious that Q8 region is less than Q8. This shows an obvious improvement in cycle thermal efficiency as everything else remains same. The work produced per unit mass flow is not altered by the use of regenerator. Here is standard cycle thermal efficiency. This is the diagram figure of regeneration gas turbine cycle.
For summary of regeneration gas turbine cycle, in a regenerative gas turbine cycle in which heat recovery is carried out by a mixture of air which is obtained by contact between water and a part of the whole of compressed air, said compressed air being compressed by a compressor for compressing gas using air or air-based gas as a combustion supporting medium gas.
Okay, for the last conclusion is, as for the conclusion, regeneration gas turbine is more adaptable to small-scale power generation system. The regeneration gas turbine cycle do not need internal heat transfer surface for heat removal. Okay, that's all from us.
So that's all from us. Thank you.